We're going to go ahead and get started. If you're not familiar, NOAA is the National Oceanic and Atmospheric Administration. It's a federal agency dedicated to understanding and predicting changes in climate, weather, oceans, and coasts. Today, we're introducing you to the fabulous forecaster, Shawn Dahl, who will be talking about space weather. But before we start, we'd like to recognize that we're all coming to you from the traditional native lands of the Arapaho, Cheyenne, and Ute. These native communities who have substantial traditional knowledge to share with us are important, and our speaker today is coming from Boulder, where those lands take place. With that, I am going to turn off my camera, and I'm going to mute myself, and I'm going to send it over to Shawn.
All right, thanks, Sarah. Welcome, everybody. It's my pleasure to be here today and talk to you about the sun and space weather, and of course, solar storms. So that said, I am a senior space weather forecaster, as mentioned, at the Space Weather Prediction Center in Boulder, Colorado. So not too far away from the mountains, actually. And if you could be here in person today, you would be walking into the heart of our building and be looking in through these two giant windows you see here on this slide, looking into the forecast operation, which is really the main event, if you will, of the Space Weather Prediction Center. And we all call this SWPC for short, and you should think of it that way as well. Now, we are part of the National Weather Service, and one of the missions in the National Weather Service is the protection of life and property. And we are, of course, very proud to be part of that mission. So, as mentioned, I do like to ask questions. So we're just going to spend maybe 5-10 seconds, let you think about it, type it in chat if you want, write it down, however you and your schools want you to do this. But we're going to go over the answer pretty quickly after I've asked it, just so you all have it, and those watching on the recording have the luxury of being able to do this for themselves as well. So we're all told that the sun is big. Well, how big is the sun? How many planet Earths could fit side by side across the center of the sun? How many of you think 50, 100, or 500 Earths could line up across the center of the sun? Well, if you thought 100, you were the closest to correct, because about 109 planet Earths could fit side by side right across the center of the sun. So if you do the math, that roughly means about 1 million Earths could fit inside of it. So the sun is gigantic. And if you like astronomy and the planets, well, Jupiter's almost 10 times bigger than Earth, so about 10 Jupiters could fit across the center of the sun. So we all know roughly how big the sun is now, but how far away is the sun? How many of you think 100 million miles, 50 million, 10 million miles? Well, any of you that are thinking or answering 100, you are the closest to correct, because the sun is about 93 million miles away from the Earth on average, as we revolve around the sun every 365 days. The distance changes a little bit because it's not a perfect orbit, but roughly on average, it's about 93 million miles away. That's a long ways away. Just how far away is that? Well, it takes light 8 minutes to get here from the sun. So if you're underneath a nice sunny sky like I am today, that light that's shining on you is actually 8 minutes old. That's amazing, because the sun, if I snapped my fingers and the sun disappeared, we wouldn't know anything happened for another 8 minutes. That's how long it takes. So when you're doing space weather forecasting, it's very hard, because you're forecasting for this giant ball of gas that's 93 million miles away. And that's tough to do. In regular weather, it's hard enough to forecast a storm, whether or not it's going to hit your town, and it's maybe 50 miles away. Where's it going to hit? How much is it going to be? Is it still going to be strong when it gets there? Think about that when it's 93 million miles away. Very difficult to do. So what exactly is this space weather? Well, it's what's happening on the sun and all that space in between the sun and the Earth, and ultimately at and around our planet. And you all know what regular weather looks like. If I said tornado, you get an image in your mind. You know what that is. You know what rain, wind, snow. You know these things. But what exactly is space weather? Well, it's this. We have things that sound like they came out of a wild science fiction movie. We have solar flares, sunspots, coronal holes, coronal mass ejections, radiation storms. These are the types of things that we are looking for as space weather forecasters, because there's a lot of people and companies and technologies that need to know about space weather because it impacts our way of life. This slide here just demonstrates a sampling of some of the many things that space weather can impact. And as you can see, there's a wide variety of things that cover huge operations, whether it's airlines flying, our ability to navigate with GNSS and GPS systems, power operations, space flight, among many other things. And this is really why we do what we do. It's to protect and inform those people that use these technologies that ultimately we use for our way of life. Now, space weather impacts things, can impact things as mentioned on the slide. But you, as long as you're on the surface of this planet of ours, you are completely safe. Anything I talk about today, you will not be physically hurt or harmed or have to take any protective action to protect yourself from a space weather storm, because we have a two-layer protection system here around our planet. We have our great atmosphere, which is our atmospheric filter screening out all the really harmful stuff that can come from the sun, let alone during a solar storm. And then we have this magnet. Earth has a strong magnet, and that strong magnet makes a very strong magnetic field. This invisible set of magnetic field lines, which act like a strong shield here, protecting us from the harmful particles that can be coming from the sun, especially during a solar storm. So between our atmospheric umbrella, that nice filter, and our strong magnetic shield, you are fully protected here on our planet. Now, if you decided in your life to be an astronaut or be a pilot or an air crew member and get up at those high altitudes, especially around the polar regions, yes, well then perhaps, as rare as it might be, there is the chance that people could be physically harmed from a space weather storm, in particular one certain type. And we're going to talk about that today as well a little bit as we progress. But like I said, you are totally safe as long as you stick to the surface of our planet. Doesn't matter if you're up on a mountaintop or down low, you will not be hurt. So let's go behind those windows you saw earlier into the forecast office. And this is what you would see. You would see this large arena of desks, monitors, computers, TVs with displays on them. And as you probably have already guessed, all these colored circles that you're seeing on the wall on those TV monitors are the sun. We're just looking at the sun at different temperatures and wavelengths of light that allow us to look a little deeper into the sun or at the outer layers of the sun. And we can only look so deep into the sun, and that is really where light finally escapes and makes its journey. That's always what we refer to as the surface of the sun, that photosphere, where photons of light finally escape into space and make their 8-minute journey here to Earth and beyond. So when I talk about the surface of the sun, that's what I'm talking about. And that's the lowest layer we can see. And then there's a few layers above it that we look at as well. And somebody's always in this office. We're always there. Somebody's staffed in there, either no matter the time of day, 24 hours a day, 7 days a week, somebody's there, whether it's Christmas Day, Easter morning, a Sunday, the middle of the night at 3 in the morning or midnight. We all take our turns rotating through, and that's what meteorologists and scientists that I work with as forecasters have to do. We have to rotate through these shifts because the sun can do something at any time. We have to be there ready to respond. And these are the types of things that we're focused on. There's many things we're looking at, as you can probably guess just from the impacts possibilities that you saw. But there's 3 main areas that we really focus on, and they're kind of impact-based. So solar radiation storms, those relate to something called a solar proton event. Radio blackouts, which relate to a solar flare. And then geomagnetic storms that relate to things called coronal mass ejections or coronal holes. We're going to cover most of these today to get you a better understanding of what storms can affect us here at Earth, which may affect your way of life down the road, depending on what you decide to do with your life. Now, how do we collect information? Well, we have to use a wide variety of tools, and those tools are usually telescopes, not like those sitting here behind me, my astronomy backyard telescopes that I use to look at planets and deep sky objects up there. but special telescopes that have these filters on them that allow just a sliver of light to come through at a certain wavelength where you can safely look at the sun. And I used to do that on the island of Puerto Rico for 4 years while I was in the Air Force. That telescope you see under that U.S. Air Force banner on this slide is mine. For 4 years, I operated that telescope and observed features on the sun and reported them not only to the Air Force, but right here to the Space Weather Prediction Center. So it's kind of funny and ironic how I've come kind of full circle from where I started. We have satellites in space that observe the sun for us. Remember I talked about our atmospheric filter screens out the really harmful stuff? Well, the only way we can look at some of those things that we need to see are by a satellite in space because the atmosphere filters it out. And we need to see that because that's how we measure some of our events, is we have to use these tools in space because our technologies, a lot of them lie in space, like those satellites and astronauts. Some of these are very close to Earth. Some of them are much further away. You can see the wide range of distances here on this slide, and they're all there for various certain types of reasons. And you'll see images from these satellites themselves here. So let's go back to the sun again. Another question for you to think about. Most people don't know this. Now, if you don't know, who cares? In science, when we don't know something, we try to learn and we come up with a hypothesis and then we have to either prove it or disprove it. That's how we learn. Sometimes we have to take a guess and then see if it's true. So what do you think? If you don't know that the sun rotated, how long do you think it takes for it to make a rotation? A month? About 2 weeks? Or a week? Well, if you were thinking closer to a month, you're the most correct because it takes about 27 days on average. I said on average. Why in the world would I say on average? That's because the equator, that middle of the sun, is rotating much faster than the polar regions of the sun, almost 10 days faster. Now that doesn't happen here on planet Earth, right? We all know that the Earth makes a rotation in 24 hours, right? Doesn't matter where you're at on planet Earth, 24 hours later, you're going to come back around and be on that same line with somebody further south or north of you. The sun doesn't work that way. So here on planet Earth, if it makes a rotation, 24 hours later, you're going to be in that same north-south line. Now, the sun is different. It can handle that stress and not break apart like Earth would if we rotated differentially. But what it does mess with is its magnetic field, because the sun has one as well, a very strong magnetic field similar to Earth's. But that's what gets messed up. It gets pulled and twisted as the sun rotates. So let's pretend the sun's magnetic field was this nice north-south line here. It never looks this way, but let's just pretend it did for a minute. So a month or two later, as the sun's rotating, that magnetic field gets pulled and stretched because it's rotating much faster here at the equator. Now this happens month after month, year after year, so that you get to where the sun maybe had been this nice north-south alignment. A month later, that magnetic field's getting pulled. A few months later, further and further, where it begins to lap itself and it wraps up year after year, and it becomes this twisted up, gnarled mess of magnetic field lines. That's the solar cycle. That's how that works. So that on average, every 11 years, during an 11-year cycle, we go from a more neutral magnetic field on the sun to this twisted up magnetic mess of field lines, all gnarled up. This happens every 11 years where we go from a maximum, that messed up magnetic field lines, back to the next maximum. And conversely, you have a minimum of activity where every 11 years, you're going to have that minimal, back to minimal activity going on. Right now, we number these solar cycles. We're now in solar cycle 25. I think the latest one on this chart is 23. We are now in 25. We're climbing up the mountain. The sun is beginning to lap itself on those magnetic field lines, and we're starting to have activity. And we're still a few years away from solar maximum. So this is an exciting, interesting time to get this talk because you're going to hear more and more about space weather over the next several years. And in particular, because of some new things that's going to be going on in space. Now, let's go back to the sun for a minute and think about magnets, because magnetism is really important when it comes to space weather and the sun. So you probably at this point have experimented with magnets, and if you haven't, you will. Certainly in textbooks, you've seen a picture like this, where I've taken my magnet and iron filings around it. You can see the invisible magnetic field lines show up that are going out one side of the magnet and coming into the other. Well, the sun, because of that differential rotation, it's not just on the surface of the sun, it's actually happening deeper inside the sun as well. And when those strong magnetic field lines in the sun that are spread out through there become twisted and coiled up together, they become lighter and they actually pop through the surface of the sun. And they kind of come up. If my hand's the photosphere, that surface, popping up through the sun will come these invisible magnetic field lines coming out and going back in. That's essentially a magnet sitting on the surface of the sun. That's what we start to look for as solar activity picks up. So that complicated image you just saw maybe looks a little more simpler if you think of these as magnets sitting on the sun, because that's what begins to show up. And if these strong magnetic fields that punch through the surface of the sun are really intense, they can reveal themselves as these things called sunspots, these giant dark blemishes which show up on the surface of the sun. Some of them can get quite large. You see the size of Earth. Remember, 109 Earths fit across the center of the sun. This is a tremendously large sunspot. There's a lot of magnetic energy there. Now, the interesting thing about sunspots is they're often the source of storms, the main source of storms, because of that strong magnetic energy that's sitting there. But let's prove about the sun rotating. I said it rotates. Let's see it rotate. This is about a month's worth of imagery from one of those satellites in space, and we can use the sunspots to show that the sun's rotating. If we didn't see sunspots, it'd be very difficult to tell that it's rotating, wouldn't it? But here we can see it. We can see how dynamic this actually is. We can see sunspots emerging. We can see them growing. We can see them shrinking, some decaying, some emerging, rotating into view, rotating out of view. These are the types of things that we analyze very closely, these sunspot groups, these active regions, because they are the source of most space weather storms. Now, when we see them, if they look like they're going to last long enough, we will give them a name, and that name is a 4-digit number. And we just raise the next one. So if we decided to number another sunspot group that you see on this picture here, it would be 3406. And look how the magnetic map is overlying where these sunspots are. So those black and white areas are the strong magnetic energies. One's negative, one's positive, and you can see how they're right in line with these sunspot groups. So once again, I'm showing you that these magnetic fields are where these sunspots could show up when they're strong enough. You can have these strong magnetic fields show up, but they're just not intense enough to give us a sunspot. And why might that be, I wonder? Well, let's think about this. And let me ask you another question as we think about this. Now that you've learned a little bit about sunspots, and if they're intense, they pop through the surface of the sun, what do you think about them? Are they a different temperature? And if so, what might that be? Are sunspots hotter than the surrounding sun? Colder than the surrounding sun? Same temperature, just a blemish, an artifact from this strong magnetic field. What are you all thinking here? Now, before I go to the answer, look at that picture on the right. You see a sunspot group. And look at that picture on the left. We're using some special imagery here to look just a little bit above the photosphere. And what are we seeing there? Are we seeing what looks like different angles of magnetic field lines? We sure are. That's because those are areas where magnetic fields are coming in out of the sun, right around a sunspot group like you see on the right. So back to the answer. What did we think? Well, if you think even cooler, you're correct. A couple of thousand degrees cooler. The surface of the sun, that photosphere, is roughly 10,000 degrees. Well, these are a couple of thousand degrees cooler. The stronger, more intense they are, probably the cooler they are. That's because they're blocking the normal transfer of energy and light and heat coming up from inside the sun, and they kind of make it go through it and between it and around it, and then you get these hotter things called active regions in and around these sunspot groups. So they're kind of tied together. You really don't often have one without the other. Now, let's look at these field lines in that imagery again we talked about. You can see them showing up here. And look, some of them are intensifying and brightening up, others not so much. But there's differential rotation going on, causing these changes where some are expanding, twisting out a little bit, brightening up. But what we're not seeing sometimes is where they're getting twisted up and stressed as well, because that's happening. Now, if you take a rubber band like I've been using here, and you stretch it and you stretch it and you stretch it because you want to shoot it across the room, if you don't let it go before you stretch it too far, what's going to happen? It's going to break, right? And then instead of shooting off, that energy is going to get released in the breakage, and it may slap and hit you in the face or your arm, and it's going to sting, right? Well, something similar happens with these strong magnetic field lines. When they get stressed out, they don't break, but they reconnect into something less stressful called a reconnection event, and that's where we get our first storm, a solar flare, this giant burst of energy because of that stressed out magnetic field, which reconnected instantly. Burst of energy across almost the entire spectrum of energy that we measure. And the stronger these are, the more intense they can be and the more impact they can have, especially on the sunlit side of our planet in those outer atmospheric layers. And these are these solar flares, and we measure them in X-ray strength, which is why we have to use a satellite in space above the atmosphere, because X-rays don't make it through our atmosphere. Now, these solar flares, they can be very quick to happen, and at their most intense, they may last a few hours to settle down. Other times they can be just last a minute or two. Quite different in how they work. Now, we as forecasters never know that a flare is about to happen. There's no science that tells us we can warn on a flare. But what we do is we analyze these regions very closely, and we try to come up with the probability that a flare could happen over the next day or three. And if it does, how intense might it get? I didn't really talk to it earlier, but when I was talking about the three main areas that we look at, there was this scale down there, this 1 through 5 scale. That's our NOAA space weather scale. When we start to get to the 1 level on these, that's where we're in our first minor level of activity, all the way up through 5, the most extreme levels. So solar flares, can't warn on them, but we can predict the probability that they'll happen. And then we alert when they do happen. It's another storm called the solar radiation storm. That's what you're seeing here on the right in that strange blue imagery. And then you see these graphs with all these elevated things, and I got these numbers 1 through 4 on there. Well, what are we looking at here? Well, when you have these reconnection events happen on the sun, this clapping of the hands, this instant de-stressing of an area of the sun, sometimes that energy can shoot outwards. And if it's strong enough, that energy that shoots outwards can shove particles ahead of it at enormous speeds. And these particles can be heavy, more massive pieces of an atom called protons. And those protons can accelerate. If they're in the right area of the sun and we have a strong enough event, they can get here in as fast as 15 to 20 minutes. Other times it may take a day or longer for them to show up, if they do at all. So very difficult to warn on these, but we can because we have a little more time. It's not speed of light, but it's close to the speed of light at their fastest. So what you're seeing here on this imagery on the right is looking at the sun from space, and then it becomes a blizzard. That's because there was a low-level proton event, a low-level solar radiation storm that impacted the sensor. Some of these satellites navigate themselves and keep oriented by using stars in space. Do you think that satellite could stay orientated if that's how it navigated itself? No way. It couldn't figure out where the stars are, right? So this can cause problems. We're going back to the moon. We're supposed to have our first woman walking on the surface of the moon maybe in 3 or 4 or 5 years. Amazing. We're going to be supporting that. We're going to be protecting those astronauts because when they're outside of our atmosphere and outside of that magnetosphere, which they will be, that protective magnet barrier, they're exposed to these. They're a threat to these. They could be harmed by these. And that's what we're going to be doing, is warning them about this activity as well. Other things that we look for on the sun are these things called filaments and prominences, these giant billions of tons of solar material, these features that extend out from the sun. And look at that giant prominence feature on the right. What does that look like? Something we've discussed already, right? Because it kind of is. That's a bunch of solar plasma trapped in invisible magnetic field lines and suspended there. These are the types of things we look for as well, because they could be the source of a solar storm. As those magnetic field lines holding it in place become twisted up and stressed out, they may become active like you're seeing on this animation here. But most of the time, nothing happens. It's a reconnection event, but it's slow, it's stable, it's quiet, nothing dramatic happens. And it just kind of gets pulled back by down gravity and rains back down to the surface of the sun. But sometimes the dramatic happens, and we can have a sudden ejection of billions of tons of material rocketing off into space, as you see in this animation. Even a solar flare happened in conjunction with that, right? That is the power of the magnetism on the sun. The more complex and stressed out and tangled up these magnetic fields are, the more mixed up they are, the more likely they are to produce an event like this. Now, we as forecasters, when we see something like this, we're immediately called to attention because now we're going to look for something in the outermost layer of the sun called the corona. Something you can see during a total solar eclipse if you're lucky enough. But we use a satellite in space 1 million miles from Earth to create an artificial eclipse so we can see the corona. Now look at this image. So what we're seeing is the satellite in space 1 million miles from Earth. That white circle is the sun's diameter. The black circle is just the disk blocking the bright sun from being seen, so we can look at that lower corona out there. Now focus on that top left of this image, that bright area there in the corona. Watch what happens. That's a time and date stamp on the bottom. So if you note that time, 9:30, look what happens in just 4 hours as you watch that top left area. That is a coronal mass ejection, or CME. Look how huge that is and how little time it took to travel a vast distance from the sun. That's because these events, when they happen, they expand as they move off into space. And they can become quick, they can be very quick, and they can be quite slow. It just depends. But what's important to remember is not only are billions of tons of material rocketing off into space, but there's a strong magnetic field that's being pulled out into space along with it from the surface of the sun or lower levels of the sun. That's what we're most interested in as forecasters. Now, that one was on the side of the sun. So you're thinking, wow, that's cool to see, but if we're looking at this from Earth, that's obviously going another direction. Well, that might be true, but these expand, and we don't have a three-dimensional look at the sun most of the time. So that could actually be more directed towards Earth than we think. At least, at the very least, 93 million miles is a lot of expansion time, right? So it could expand and actually clip Earth off to the side, perhaps. So we still take note, and we still analyze and forecast these and put them into our watches or warning forecasts as needed. But sometimes it's a little bit more obvious, and you can get something called a full halo CME. Okay, that's only going one of two directions, either away from the sun, away from Earth, or towards Earth. You may wonder, well, duh, that should be easy to figure out. No, not necessarily. When we're at solar maximum, as many sunspots as we're seeing on our side of the sun are facing the other direction as well. And there's hordes of activity that can be going off. CMEs can be shooting off all around the sphere of the sun. That's where our other tools like radio observatories and all the observations and tools that we have come into play to help us figure out whether a CME like this is coming towards Earth or going away. So what's the importance of these? Well, as the strong magnetic field sends out into space and comes towards Earth, it's going to collide with our magnetic barrier. That magnetic shield called our magnetosphere. The front of it is in particular is what we're looking for here when they arrive. Now, this is where magnetism once again becomes very important. Earth's magnetic field is orientated like this. Positive pole down to the south. So the magnetic field lines are coming out the bottom of the planet and going into the top. So a thumbs up orientation, okay? Now, when CMEs come from the sun, if it's dragging that strong magnetic field with it, right, and it happens to be oriented the same direction as Earth, what's going to happen? Well, you have all probably played with magnets already at this point, right? If I take a magnetic that's orientated like this, like Earth's, and here comes the CME, and it's orientated the same direction as Earth. When that arrives here, what are these magnets going to do, buddy? If I let my finger off there a little bit, what's going to happen? Are they going to stay together? Let's see. It repels, right? But if that magnetic field coming from the sun is opposite Earth's, and it hits here, okay, if I let my fingers go now, what's going to happen? They stay together. They're connected, right? Same thing with these strong magnetic fields and these CMEs coming towards Earth. If they're orientated in that thumbs up direction, not much is going to happen. If it's the opposite, boom, the connection happens. They become one. We become almost entwined with the sun's magnetic field, And that's when we get these things called geomagnetic storms, which create a huge number of effects that so many people are interested in. And you are interested in them as well, because that's what drives the aurora, those northern lights that we loved and had a chance in our life to see at some point. I'm from North Dakota. I've seen these a few times. I don't know if any of you have or not, but if you get the chance, you're going to want to check these out because they can be quite spectacular. That picture on the bottom right was from an astronaut in space at the space station, looking down on the northern lights. That's pretty cool. Now, that space weather scale I was talking about, if you ever hear about us predicting a G4 storm, that 4 or 5, that top level on our scale, it's time to pay attention here in Colorado. And depending on where you're listening to this or joining in from, the stronger that number on that scale, the more chances you have of seeing it the further south from the normal areas that these happen. You have to see. So that's been a lot of information, a lot to talk about, but I have one last question for you. Let's just see how much you understood or were listening or had a chance to think about. Let me ask you a forecaster question based on what you've seen and learned today. Here's 2 sunspot groups from the sun. 2674 up north, 2673 down south. So what we see on the right is a colored magnetic map. Instead of it being black and white, it's in color here. So the reds and the yellows represent negative polarities, and the blues and the greens represent positive polarities. So look close at these 2 pictures. The sunspot groups themselves, 74, is pretty long, right? Looks like there's a lot of spots spread out in there. Huge section on one side, another large section at the other end. And then we got 73, this one giant cluster of spots there. Which of these might be better likely to produce a flare? And if you look at that magnetic map, maybe that gives you another clue. Which one has a more clear defining line between the magnetic fields? Which one looks a lot more mixed up? What do you all think? If you had to make the forecast right now, you needed to get it out in the next 2 minutes, which of these regions would be the most likely to produce a solar flare, do you think, based off this fast lesson that you've had today? Well, if you thought region 2673, you are the most correct, because that produced the largest flare that we had the last solar cycle in 24 and one of the largest since measurements began. So if you guessed that, fantastic. If you didn't, so what? That's how we learn, right? It's okay to make mistakes. But that's been my pleasure to talk to you, and we've got enough time here to take on some questions if you have them.
Yeah, so feel free to drop questions in chat if you have them. Shawn, can you tell us a little bit about your background? How did you become a forecaster?
Yeah, I had a very long, crazy path to get to do what I'm doing. Most people to get to be something that I'm doing right now as a space weather forecaster would go through college and get their master's, if not their doctorate degree. Me, I was in the Air Force for 22 years, and I continued my education through the Air Force, and I actually got to do this in the Air Force. So between that college education and that experience level that I have, I was able to take a long journey to get here where I am today.
That's pretty awesome. I was just down in the Space Weather Forecast office this morning, and I found out that there are colleges that are starting to offer space weather classwork. So you can actually potentially take this in college one day, which is pretty cool. So we did have a question. How do sunspots get named? Who gets to name sunspots?
Yeah, that's us. We get to do it here at SWPC. We decide that there's a sunspot group that looks like it's going to last the majority of a day, and we get some of our solar observatories reporting them, so we have that information. Then we decide to go ahead and give it that next 4-digit number. Now, it might be 0001, or it could be wherever we're at right now. But we do it, and once we do it, the rest of the world that does this type of work recognizes that, and they all call it one and the same.
That's pretty cool. I want to name a sunspot. So on your past slide, I think they're talking about 2673, and they were wondering, why did it flare first, or why would it flare first?
Right, they're most likely to do it. Doesn't mean it would be the one. It could have been 74 as well. That's why either one is actually a right answer. But for our purposes as forecasting, 73 was the most likely. And the main reason for that is that magnetic map. There's quite a bit of mixed up magnetic fields there. We see blues and reds next to each other. We see some reds further out. If we look really close at that region, or if you get the chance to look at it closer, you can see that there's more mixed up polarities close together, as opposed to 74, which has a pretty clear dividing line, almost like my magnet right here. Got the reds on one side and the blues on the other side. That means there's not much stress there. It's a pretty clear line. But if these are all bent together and mixed up, that's why it's most likely to do it. In this case, that's probably why it did.
Very cool. We have 2 CME questions. So the first one is, how does James Webb handle CMEs?
I don't know yet. We're not getting the information to us yet. They're still doing all their research and science, but we're hoping that at some point we'll start to get information from that telescope if and ever they decide to use it to look at anything towards the sun. Right now, they're doing all their cool astronomy, like my telescopes back here.
And the other question is, what effects, other than the northern light, full low sea cause?
Yeah, you broke up quite a bit there. I think I caught the gist of it. Yeah, the CMEs, when they arrive at Earth, other than driving the northern lights further south, they can start to work on our atmosphere. So basically all the interactions going on, many things are going on. One is we get instant reactions because our magnetic field gets pushed when these arrive. And that's not from the magnetic, that's from that solar material punching in, because they can come in pretty fast. So they push our magnetic barrier closer to Earth. And when that happens, that drives natural electrical currents which go around our planet more and more. So all sorts of interesting things begin to happen in these normal currents. And if they're strong enough events, they can actually work their way down into the power grid of our country and around the world, where they start to show up on electric lines as extra energy. But it's extra energy that we don't want. The world operates on alternating current. These introduce direct current, and you don't want those on the same system because they can cause massive problems. And in the most extreme activity, the concern is that they could actually cause a region or large area blackout, meaning more than just a town, but like states, for instance, across a good chunk of our country. They also affect GPS systems on the ability to navigate because of the things that change in our atmosphere. They don't go as fast as they normally do. They change around. They can cause the atmosphere to heat up. And so satellites that are out there orbiting, they have to use up their fuel to burn a little bit so they don't get pulled down, because as the atmosphere heats up, it expands, and then this slows the satellites down. So they have to burn some fuel to keep them at their orbital point.
And this is a question that you kind of touched on earlier. What damage can solar storms do to your body if you are in space when they're happening?
Yeah, like I said, on planet Earth, you're good to go. No concerns. If you're on Mount Everest, no concern. Nothing's going to happen to you. But if you become an astronaut or become a pilot or an aircrew member that's flying at those high altitudes, very high altitudes, or near the polar regions, that's when these solar protons, these energetic protons, these solar radiation, they can penetrate on those outer layers of our atmosphere, and certainly outside of our atmosphere, right? And that's where you can be directly exposed to these. Now, it would take a pretty strong one still to harm anybody up there, but that's what starts to drive that radiation, where these particles penetrate the tissues in your body and cause radiation sickness.
Well, I know you guys have been working very closely with NASA because NASA wants to go to the moon and to Mars. What are some of the things that NASA is thinking about doing to help protect astronauts from these storms and this radiation?
Yes, many of you probably have heard the phrase, if you're caught in a lightning storm, what does the Weather Service tell you you're supposed to do if you're caught outside in a lightning storm? Have you heard the phrase duck and cover? If you've heard that phrase, great. If you haven't, that's what you're supposed to do if you're caught outside. You're not supposed to go under a tree. That's the worst thing you can do. You're supposed to get low to the ground and cover. Well, guess what? Believe it or not, these poor astronauts out there, when they're out there in their tiny little capsule, traveling out there towards the moon, okay, they have very little protection. Because for one, they're not in their full spacesuit while they're in that capsule. You've seen pictures of astronauts on the space station, right? Are they in their helmets and everything when they're in? No, they're not. They're just in their flight suit, if you will. So they don't have a lot of protection. So what I'm told, I don't know for sure, but what I've heard in the meetings we've had with them is it sounds like they have to build, using some material that's in there, create kind of this little artificial barrier, almost like a box. and they have to get low in there and get as low as possible, tight up, and just stay in that position until the storm is over. Now, these storms can last for hours. At these intensity levels that it's going to take for them to have to do that, though, it'd probably be shorter than days, but it still could be hours. So we're going to have to not only learn how to predict the possibility that these are going to happen better, which we already do, we just need to get better. We're also going to have to predict when they end so that they know they got the all clear to come out of that safe hold position, if you will.
Well, thank you, Shawn, and thank you to everyone that signed on today. We hope you learned a little bit about space weather and that maybe one day you'll come work with us and Shawn in the Space Weather Forecast office. If you have any additional questions, you're always welcome to reach out to Carolyn and we will make sure that Shawn gets those questions. So thank you so much and have a great rest of all of your day.